Thanks, Jimmy. Hi, I'm Matt McEwen. I'm a student researcher at the Google Quantum AI team and a PhD student at the University of California, Santa Barbara. And today I'm going to be telling you about some recent work we've done on what happens when high-energy particles impact our quantum processes. As we're starting to make larger and more complex systems, as we're scaling up, we have to start worrying about more and more exotic forms of error. So high-energy radiation is actually all around us. From the materials we make our fridges, wiring, chips, and even buildings out of, all of these have trace amounts of radioactive impurities. These levels are far too low to worry humans, but for sensitive electronics, especially including detectors for astronomy and high-energy particle physics, this is a well-known source of error. In addition to that, other sources of high-energy radiation include the kind of soil beneath us and space above us in the form of cosmic rays, which are very hard to shield against. So for our quantum processes, this is an important thing for us to understand. But in order for us to understand this error source, first we have to be able to find it. So we do that by using basically operating our quantum processor a lot like a particle detector. Using recent advances in state preparation and measurement, we can very rapidly interrogate the qubits, finding out whether they've experienced an anomalous error event. If we tile that over a large number of qubits, and repeat it over very long periods of time, we can go looking for anomalous events. Most of the time, the errors on the qubits are effectively independent. There's a low background error rate just due to imperfections in the qubits themselves. But if we run one of these experiments, we find events like what's shown here on the right, where suddenly the amount of error on the device jumps from a low background up to a really high number, almost all of the qubits on the device decaying at the same time. We can also see here that the return to equilibrium is on a really long time scale for a quantum processor. So the exponential decay constant for this event is around 20 milliseconds, where typical experiments take microseconds. So this is a really severe correlated event, exactly the kind of error event that quantum error correction is not naturally suited to fixing. So if you're an experimentalist and you found something interesting or concerning, the next step is to take a lot of data. So we can take long runs of these experiments and use filtering to remove the well-understood background error to really clearly identify these anomalous error events. And we can see a couple of things immediately. First is that they're sort of randomly distributed in time. Sometimes we can go for 60 seconds without seeing one of these events, but sometimes they're clustered a lot more closely than that. And the other thing we can see is there's significant variation in the scale of these impact events. We can look at the time distribution more clearly by plotting out the distribution of the time between adjacent events. And here we can see that, as you would expect for kind of independent particles striking a chip, it corresponds to a Poisson process, with the average time between events being around 1 every 10 seconds. So basically what we've discovered so far is that our quantum processors experience large correlated error events that last for a really long time and happen once every 10 seconds. This is a significant problem for our plans for error correction. So if we want to handle these physics events, we're going to have to understand what is happening in the chip so we can try and mitigate it. So next, I'm going to take you through the story of an impact event. What happens when a high-energy particle passes through our chip? Well, what happens is it deposits a lot of energy, mostly in the substrate of the chip, in the silicon itself. Now, that energy rapidly scatters into ballistic, high-speed phonons, effectively like a shock wave that moves through the substrate until it interacts with the superconducting qubit layer. When it arrives there, it has enough energy to break up the superconducting condensate, producing quasiparticles. These quasiparticles then scatter and produce additional phonons. And so as the event progresses, energy moves between the quasiparticle population and the phonon population as it spreads out through the device. But it's the quasiparticle population that we're especially concerned about. And the reason for that is an effect called quasiparticle poisoning. Quasiparticles are abusively non-superconducting electrons living inside our qubit. And because they're non-superconducting, they're pretty happy to scatter and disperse energy. They're also happy to tunnel across the Josephson junction at the heart of the superconducting qubit, along with the supercurrent that makes up the qubit state. When it does that, there's a really strong coupling between the two. And that effectively allows the quasiparticle to steal the qubit's energy, causing a decay event and destroying our qubit state. So two key predictions from this physics story, from the theoretical modeling we've done, is that we should be able to find a localized impact event that subsequently spreads out quite quickly over the device, And second is that the error mechanism itself should be a severe T1 decay error due to the quasiparticle poisoning, meaning there should be an exponential sensitivity to the sampling time of our error source. So using the speed of our detector quantum processor, we can indeed find this localized impact and spreading out. So here you can see an impact happening on the right side of the device, inducing a lot of error across the qubit patch. We can see that there is a small rising time associated with the event starting and spreading out, as well as the kind of slow decay time we've seen before. And we can actually do this analysis for a number of different events and see that the localization is different depending on where the particle passes through the chip. One particularly interesting one here is, again, the one on the far right, because this event happens a significant distance away from the qubit patch, but still the error and energy is able to travel a significant distance and still induce a lot of error in our chip. And so the other key prediction we'd like to confirm is the event mechanism itself. So as I said, for quasiparticle poisoning, there should be an exponential relationship between the sampling time, our sensitivity to the error, and the error we find. Using the speed of our metrology technique, we can interleave experiments with different sensitivities. So for the same event, we can measure at different sampling times. And we do extract a exponential scaling, which gives us some confidence we understand the error mechanism. It also gives us a good view of the magnitude of one of these events. We can re-express the size of the error in terms of what it's done to the coherence time of the qubits. For this chip, the average coherence time over the qubits was 14 microseconds when they're all working properly. But during one of these events, it drops to less than 1 microsecond. And it stays that way for sort of milliseconds at a time. And so this is really concerning because 1 microsecond is an important number. It's the typical cycle time for a QEC experiment. So we can understand that an event like this is not going to be correctable, survivable by a QEC code. Now, that being said, now that we understand the underlying physics, we need to think about mitigating these events in our devices. And actually, we've got a lot of work from other fields that we can that can help us here. So as I said before, this is sort of a well-understood error source for detectors, both high-energy particle physics detectors and large-scale astronomical detectors, which are actually built in a very similar way to our qubit chips. So this is an example of a large-scale MKID telescope detector made of superconducting resonators, where they also see highly correlated error events. And they've deployed some techniques, including backside absorbers, which effectively suck up the phonons, preventing them reaching the sensitive device, as well as changing structures on the chips, including barriers and membranes, to prevent the phonons spreading the energy over such large distances. So these techniques are well within our capabilities as well, although we're now presented with a really interesting challenge of how to integrate these mitigation structures into a highly complex and large-scale quantum chip without reducing the gate coherences or the coherence times we've already achieved. So in summary, overall, we found a really interesting physics problem. High-energy radiation produces highly correlated and therefore difficult to correct error events on our chips. But using the metrology techniques we've developed, we think we understand the underlying physics, and we think we understand how to improve our devices for the future to enable us to move towards our goal of scaling quantum error correction up. And with that, I'd like to thank the Quantum AI team for all of their support with all of this work. And next up, I'd like to introduce Jens Paulsberg from UCLA.